So far, the course has watched one random variable at a time. Real models rarely have that luxury. A signal comes with its noise, a first draw with a second. This chapter puts several random variables on screen at once. In this video, we meet the object that describes a pair completely, the joint probability mass function, best pictured as a table of masses. Learn to recover each variable's own PMF by summing the table out, and see why the margins alone can never tell the whole story. And then push functions and expectations through the pair, ending at one of the most useful facts in probability. Take two random variables riding the same experiment. Together they form a pair. Each outcome in the sample space now lands on a point in the plane, an x-coordinate from x, a y-coordinate from y. The pair is described by one function, the joint probability mass function. P sub x comma y of x and y is the probability that x equals x and at the same time y equals y. It is the one variable definition with the event replaced by an intersection. And the familiar rules carry over. The probability that the pair lands in any set of points is the sum of the joint masses over that set, and summing over every pair of values gives exactly 1. Here is a joint PMF worth staring at. An urn holds balls numbered 1, 2, and 3. We draw 2 without replacement. X is the first number, Y the second. The table shows every mass, zeros on the diagonal. The same ball cannot appear twice, and 1/6 in every other cell. What is the PMF of X alone? Fix a row and add across it. 1/6 plus 1/6 is 1/3 for every row. That operation, summing out the variable you don't care about, is called marginalization, and the result is the marginal PMF of X. Columns work the same way, and Y's marginal is also uniform, 1/3, 1/3, 1/3. The margins of the table, literally the sums written in its margins, are the individual distributions. Now change one word in the experiment, draw the two balls with replacement. The table transforms. Every cell becomes 1/9 diagonal included because the first ball goes back before the second draw. Sum the rows and columns, 1/3 everywhere. The marginals are exactly the same as before. Same margins, different tables. And that is the lesson. The marginal PMFs do not determine the joint PMF. Whether the two draws can collide, whether they push each other around, dependence lives inside the table. In information, the margins simply do not carry. To describe a pair, you need the joint. Functions ride along exactly as they did for one variable. Roll a blue die and a red die and let U be their sum. U is a random variable, and its PMF sums the joint over the pairs that produce each value, the diagonals of the 6x6 table. 2 comes from one pair, 7 from 6 pairs, and 12 again from a single pair. The familiar triangle of the two dice sum, straight from the joint. Expectations follow the same pattern one dimension up. The expected value of g of x and y is a double sum, g of each pair, weighted by the joint mass of that pair. Now take the simplest g, the sum, split x plus y inside the double sum, and it falls apart into two single sums, each one a marginal mean. The expectation of x plus y is the expectation of x plus the expectation of y. Look at what we did not assume. Nothing. No independence, no special structure. Linearity of expectation holds for every pair, always. For instance, in an urn with 3 balls, the expectation for a pair of drawings is 2 plus 2, 4, with and without replacement. The key idea of this video, the joint PMF is the whole story of a pair, marginals sum it out, and expectations of sums split with no questions asked.